Hi everyone. This is going to be the last sort of new topic in this Unit 4 on systems of equations. It's actually not a new topic. The question, how many solutions, is a question that we almost started the unit with. You'll remember from our Desmos activity, the big race, we had 3 different racing scenarios. The first racing scenario was kind of our normal racing scenario, the one we've gotten really used to. And in this case, the red and the blue lines represent a system of 2 equations, and the solution is this point that's on both equations, on both lines. And that would represent the solution to that system of equations. So that's the scenario in which our system of equations has one solution. But we also investigated a different scenario. In this scenario, I believe there were 2 racers named Cora and Devin. And Cora and Devin started in different places, but they ran the same speed. And so these 2 lines had the same slope, and they never intersected. And because those 2 lines never intersected, there is no XY pair that would solve both lines' equations at the same time. So there would be no solution to this system of equations. You'll note that in the first case of one solution, the lines have different starting values. So one person starts at the starting line, Alice, I believe, and then Bart got a head start. But they had different speeds, so they had different slopes. Their lines had different slopes. In this second scenario with no solution, Cora got this head start in red, and Devin started from the starting line. So they had different starting values. So the 2 lines had different y-intercepts. However, because they ran the same speed, the 2 lines did not have different slopes. They had the same slope. And that meant that the 2 lines had the same steepness, pointed in the same direction, and would never cross each other. Our third situation involved 2 twins. I think they were called Evie and Frankie. And this was a weird situation in which Evie started at the starting line and Frankie started at the starting line, and they ran the same speed as each other. So these 2 lines describing the 2 different runners, are in fact identical lines. They turned out to be the same line. So they have the same y-intercept because they're the same line. They have the same slope because they're the same line. Evie and Frankie run at the same speed. And they have the same set of points. Every point on one line is also a point on the other line. So any solution to one line's equation is also a solution to the other line's equation. So there are infinitely many points on the 2 lines that could solve either equation. And these are the 3 scenarios when we're working on systems of linear equations that we might run into. And what we need to look at next is what happens when we work with the equations of 2 lines and how the different possibilities appear when we're working with the equations. So a little reminder of how working with single variable equations looks. So first of all, we have our sort of normal type situation. For example, x plus 2 equals 10. You can subtract 2 from both sides, and you can see that x equals 8, and that's our solution. And you can clearly see that the only number that can add to 2 to make 10 is 8. So there's really only one solution to this equation, And we know how that looks when we're working with the equation, is that if we do our manipulation, we're going to get the variable alone on one side of the equal sign and a number alone on the other, and that'll be clear to us then what the solution is. But there's another situation that we ran into. For example, so let's take the example of 2x plus 6 is equal to 2 times the quantity x plus 4. Now if I want to go about solving this equation, I might draw my little golden road. And I might think to myself, the first thing I'll do is distribute on the right hand side to get 2 times x plus 2 times 4, which is 8. Now I have 2x plus 6 equals 2x plus 8. And you can start to see that there might be an issue here. So maybe I'll go ahead and subtract 2x from both sides to combine all my like terms on one side of the equation. So I get 0 plus 6 on the left-hand side and 0 plus 8 on the right-hand side. And all of a sudden, I have this kind of situation. 6 equals 8, which is not true. And so, this is what it looks like when there's no solution to a single variable equation. Okay? And as another example, I'll just show you, for instance, here. So consider the weird idea of, say, x plus 2 equals x plus 3. This is the sort of thing that happened here, but a little bit more simple. If x is some number, like say the amount of money you have, and you have $5, it's impossible for you to have $5, and then if you add $2 to the amount of money you have, it would be the same to you as if you were to add $3 to the amount of money you have. There's no way to get x plus 2 to be equal to x plus 3. There's no number that can go in here and here at the same time and make the left and right hand equal. So there's no possible solution to this equation. And it's similar over here. You can't have 2 times x and then add 6 and have that be equal to whatever 2 times x is when you add 8. So if you work with a single variable equation and you get a result like 6 equals 8, which is patently not true in the mathematics we're studying, I don't know if it's true in any mathematics, then that's a clue that you either made a mistake, which happens, or the equation you're working on doesn't have a solution. I know, and we've talked about this before we did distance learning, I know some people, when they learned about no solution, got really tempted to write no solution whenever they didn't like an equation or whenever it seemed hard. No solution is very specific. It doesn't mean, oh, this is hard, or I don't know how to do it. It means there's no way to get the left side to come out equal to the right side, no matter what you plug in for the variable. Okay? But there was also a third type of outcome with our single variable equations. So, 2x plus 3 minus x is equal to x plus 3. Now this left side looks awful ugly. Let's organize all our x's together and then combine like terms to get x plus 3 on the left. And now I can see the left side and the right side look like they're exactly the same. Okay? So if I wanted to, for instance, subtract 3 from both sides, I would get x equals x. And that means any number I plug in here is also the number I plug in here. And so any value for x could work. Alternatively, instead of, say, subtracting 3 from both sides, I could try to subtract x from both sides, in which case I get this result, 3 equals 3. And now there's no x even in there. It doesn't matter what x was. No matter what x was before we subtracted x from both sides, we still get a satisfied equation. So, this is very different, this scenario, from the one above. It's kind of like the opposite in a way. In the one above, no matter what we plug in for x, we can't possibly satisfy this equation, and same over here. No matter what we plug in for x, this equation will always be dissatisfied. But down here, no matter what we plug in for x, the left and the right will always be equal, and the equation will always be satisfied. And that means, in a linear single variable equation, that means not just that we have infinite solutions for x, but something real special for this case, which is that x can be any number we want. So x can be any real number. Maybe there are some other kinds of made-up numbers that we haven't thought of yet in our class, imaginary number of some kind, some weird numbers with spooky properties that we won't talk about in this course. But any real number like 5 or 6.3 or -4/10 or pi or whatever, simplified, unsimplified, rational, or irrational, any real number could be plugged in for x, and as long as you do it correctly, the equation will be satisfied. So these are the sort of three scenarios that could happen with single variable equations. And they're parallel to what happened with our systems of linear equations. So you can see they're not identical, but they are parallel. In our systems of equations, we could have one solution, we could have no solutions, or the third option was not any real number, but just infinite solutions. And the infinite solutions situation looks a little bit different for a system of equations than the any real number outcome looks for single variable equations. But the way that it looks when we're working with the equations is very similar. And so I'm just going to release a couple examples in a second video in which I try to solve systems of equations with substitution or elimination, and I get some results like this.